Yesterday we have seen how we could do such a fairly good prediction simply by applying two differencing filters to the original data, differencing at lag 1 and at lag 16. What we will see today is how we can use, therefore, filters, and from the filtered operation, how can we go back? So for that, we will need to do a bit of theory, very minimal theory, but that will help us understand what we're doing when we're using filter. Here's a formal definition of the filters that I've introduced yesterday informally. So a filter is a mapping from the set of finite vectors, and one filter of interest that plays a central role is called the backshift operator. The backshift is simply the one that goes back in time. So if I have a sequence X, like this one, if I apply the backshift, I obtain this, given by this formula. The backshift of X at time t is X at time t minus 1. So at time 2, it's X1, and at time 1, well, it is what is out of bound. With the convention we have in this minimal theory of filters, we set everything that's out of bound to 0. So that allows to define correctly and simply what it is. So that's the backshift operator. Right? We can view it as a matrix. A filter is in fact a matrix if we decide the size of the vector to which we apply it. If we apply it to vectors of line 6, here is what the backshift operator is. Is there anything special you can say about this matrix? It is not invertible. Anything else? Well, it has 0. It's a triangular one, like all the matrices of all the filters we will see. If we square it, if we apply the backshift twice, right, we obtain the formula. The backshift twice looks for x of t minus 2, and in matrix form, it will give this one. So what happens when we square this matrix that corresponds to B? This subdiagonal sequence of 1s is shifted by 1. Right? So if we do it n times, so here if we do it, so this is B, B squared, B3, B, so B, B squared, B3, B4 in that example will be equal to 0. Right? So if we shift enough B's, the matrix B, when we instantiate over a finite length n, then if n is large enough, it will get to 0. Right? This is why the theory of filters of finite length is completely simple, because we don't have to deal with infinity, with convergence of series and things like this. If we take an infinite series of B's, whenever we instantiate over filters of a given length, it's only the powers of B that are below some level that are non-zero. Right? It's called a nilpotent matrix, and this is why we don't have to worry about convergence, what it means to have an infinite series. Right? So there is an apparent paradox that the filters are often given by an infinite impulse response, as we will discuss in a minute, but in fact, we never deal with infinite things in this simple setting here. Here is more concretely what I said. A filter, when I say filter, it really means causal in this setting, is any mapping from like B, but except that B was very specific. In general, a filter is represented by a matrix when we apply it to vectors of length up to n. And the properties of this matrix are the ones we have seen so far. It is lower triangular. That corresponds to which property of the filter? Causality, exactly. Because the element ij of the filter is how much the output at time j corresponds on the input at time I. The output at time I corresponds to the input at time j. So if we are at time 2, for example, then we don't depend on things that were at those instances here. So that's the first thing. The second thing, we see that H2, H1 is found here, and the same coefficient is found here. This is which property of the filter? Time invariance, which is in this formula here. What happens on time t depends on what happens at time t minus 1 by a coefficient that is only a function of the difference between t and t minus 1. How t depends on t minus 1 is the same regardless of t. 3 depends on 2 in the same way as 202 depends on 200, 203 depends on 202. So those two properties automatically lead us to a matrix of this kind. Right? So a matrix of this kind has lots of nice properties. In particular, we can exactly describing by giving the sequence of the first column, for example, H0, H1, H2, Hn minus 1, which a priori is an infinite sequence, because I can apply it to a filter of any length, of length 1, or 10, or a million, or a zillion, or a quadrillion. So a priori, there's no limit on that. But remember, whenever we will apply it in practice to a filter, we will use only a truncation of this. This sequence of H has a name. It is called the impulse response. And we will see why in a few minutes. So this is our first way of defining a filter. We can define a filter by a potentially infinite sequence of coefficients called the impulse response. And our first definition of this impulse response is what I can call here the filter equation. It tells us that the output at time t is equal to H0, the input at time t, plus H1 at time t minus 1, etc., until the end, which ends when we are at the first element of the vector here. For example, if I consider the filter given by this equation, yt is 3xt minus 2xt minus 1 plus xt minus 2. That's all, right? The impulse response is 3 minus 2 plus 1, and then 0 everywhere, right? Which I read here in matrix form as the first column, and then the following columns are just repetition of the same here. So far, that's nothing very exciting. Here, when we see filters, we will usually not see this matrix, or very often not even, sometimes we'll see this equation. Most of the time we'll not see this matrix. Instead, we will have what is called an operator notation. To go to the operator notation, let me use the standard linear algebra notation. If I omit for a second the fact that the length n needs to be specified, if I ignore that, I can write that the matrix of the filter is equal to 3 times a matrix that has 1s everywhere in the diagonal. That's called the identity matrix. Minus 2 times a matrix that has 1 everywhere below the first diagonal, which is exactly the backshift operator we see, minus 2b, plus 1 b2, b squared, which is the backshift operator applied twice. So that's another way to write exactly the same equation here. I'm saying the output is equal to 3 times the input minus 2 times the input shifted backwards plus 1 time the input shifted backwards twice, which is simply saying xt minus 2. For some reasons, when signal processing, people don't use this notation, they use this one here. They say identity, they write as 1, because it's the neutral element of the multiplication of filters. So they will write f is 3 minus 2b plus b2, b squared. This is the notation that you will find everywhere in all documentations about filters. Not only, sometimes we find another one, but that's a very frequent one. I mentioned the impulse response as a sequence of coefficients. Why can we call it the impulse response? In discrete time, the impulse is simply the signal that is equal to 1 at the first element and 0 everywhere. So we jump and then we stop. Then if we apply this to the matrix, we obtain the first column of the matrix. This is linear algebra 101, so which is the impulse, which is the set of coefficients. So this is why it is called the impulse response, right? Which is not just a terminology issue. It means if you want the coefficients H0, H1 of the filters, and we'll see there are lots of instances when we do forecasting where we want those coefficients. If you have an algorithmic way of computing the action of the filter on a signal, on a vector, then you apply this to the impulse vector. That will give you the set of coefficients. So it's not just a definition, it's also something to remember in practice here. Inverting a filter. We saw some filters can be inverted, like delta 1, delta S. Some cannot, like B, the backshift operator. When can a filter be inverted? Well, the answer is easy. If we look at this matrix here, this is a triangular matrix. Right? When is a triangular matrix invertible? When all diagonal elements are non-zero, exactly. On the diagonal of a triangular matrix, we read the eigenvalues, so they should all be non-zero here. So they're all the same in the case of a filter. So a filter is invertible if its first element of the impulse response is non-zero. That's the only condition. All filters that have non-zero first element of the impulse response are invertible. For example, delta 1, which is the difference operator, in traditional filter operation, it is 1 minus B, identity minus the backshift here. Because of the 1 here, it is invertible. Here is a catalog of filters and the corresponding notation here. I omit the matrix notation because I would not fit on this table. So a general filter that does nothing would be called the identity. It is noted with 1, and its impulse response is 1, 0, 0. Right? The backshift filter corresponds to t minus 1 in time, and the impulse response will give 0, 1, 1. The differencing filter that we've seen yesterday corresponds to this impulse response. The differencing at lag S. The Roberts-Seasoneling filter, which takes the integral over a period, corresponds to an impulse response that has 1 over the first S elements, etc. Here, when a filter is invertible, when its H0 is non-zero, the inverse is denoted 1 over F, which is weird. Usually if we have a matrix A, and how do you write the inverse? A to the power minus 1. Why don't we write 1 over A for a matrix? Because? Well, why don't we write identity divided over A? Well, if A is invertible, division is multiplying by A minus 1. Here it's the same. I mean, if F H0 is equal to 0, 1 over F is not defined. Right? For numbers, it's the same. If a number x is equal to 0, 1 over x is not defined. But why is it not done to write the matrix A divided by B is A over B? Why don't we do that?
Because A inverse B is different from B times A inverse.
Exactly, because B minus 1A usually is not the same as A B minus 1, because the multiplication of matrices is not commutative. The order matters. When I write A over B or 1 over F, there is no order. I'm not saying whether it's 1 multiplied by the inverse of F or F multiplied by the inverse of 1. So if I use this notation, it must be that the order does not matter. Otherwise, I'll have a problem. In MATLAB, there is an operation, A divided by B, but then you have a slash in one order, which is not the same as B divided by A, right? You don't write in 2D like this here. Here we will see why in a minute, but this is very often used. For example, if xt is this filter here, then if f is this filter, 1 over f is the inverse. An interesting thing to know about the inverse is that it's very easy. It corresponds also to something very useful in terms of the equation of the filter. If I have the equation here that says y is the input, for some reason I'm using y as input, and x is the output. So this is the input-output equation of this filter with this impulse response. If I have to invert it, there is a very simple way to invert it if I allow recursive computation. Because h0 is non-zero, I can divide by h0, and I can compute y as a function of x and of the previous y's here, which is what I did here. Yt is 1 over h0 xt minus h1 over h0 yt minus 1, etc. So the inverse filter can be at least computed simply in this form. By iteratively, once I have computed the first elements, I can compute the next. But in general, filters do commute, as we have mentioned already. Right? So this is why the notation 1 over f makes sense, because we don't need to worry whether it's 1 divided by f or with f first, the division first or after here. So in general, f times g, not in general, for any two filters, f times g is g times f. Why is it? Well, it is because any filter, like this one here, is, like all those filters, they are, all the filters that are written here are polynomials in B. So if I take the product of two polynomials, the power b power a, b power n times b power m, that commutes, right? Because this is b to the power n plus m. The powers of b commute with each other. So if I have two filters that are polynomial in B, obviously they commute. Now a general filter has an apparently infinite sum, but that doesn't matter. When I apply it to a given signal, I can stop at some level, so I can consider as if the filter was a polynomial in B. So because filters are all polynomial in the same root polynomial, which is B, the backshift operator, same filter, which is the backshift filter, then they commute. Right? That is what makes filter calculus way more easy than standard linear algebra. Therefore, we can write g over f, and that means gf minus 1 or f minus 1g, because both are equal. Of course, when we do an operation of filter, like g over f, here it means the composition. The sum means the traditional algebraic sum. That's f plus g of x at time t is the filter f applied to x at time t plus the filter g applied to x at time t. So let's test your deciphering of this notation. Small quiz. And obviously, both A and B are correct. That was easy. This is just an immediate application of what we saw. Another one. And the majority says B, which is incorrect. So here, of course, sometimes I use y, sometimes x as input. So here the input is x and the output is y. So this is an input-output equation, which is in the reverse order. I'm giving the input as a function of the output, which of course is easy to invert, at least recursively. Yt is equal to xt plus 3yt minus 1 minus 2 here. Now that means this filter is the inverse of the filter that would have this input-output equation where x would be the output here, which is 1 minus 3b plus 2b squared. So it's the inverse of it, so A is correct. The impulse response of f is no, this is not this. This is the impulse response of the inverse filter. So it would be too magical if the impulse response of a filter is equal to the impulse response of the inverse. How do we get the impulse response of the inverse? Well, we can do the computation. How do we do the computation of the impulse response? Right? How would you do that? There's a solution on the board. That's probably not the easier one. Well, one solution is if I have a MATLAB formula that we'll see in a second to compute this filter, I take x as the impulse response. If I want, let's say, the 1,000 first items, I put x equal to the vector that has 1 at this first element and zeros everywhere. I apply the filter, and the output will be the impulse response of the filter. But there are lots of other tricks we can do. We can use also power series expansion by saying that if we do a power series expansion of this as a function of b here, we will obtain something like this. So 1 over 1 minus 3b plus 2b squared is equal to that, plus, of course, it's an infinite power series. Here I've just used usual tricks we learn in Analysis 101 to compute 1 over the limited development or power series expansion. So this is what I would obtain. Why does it apply here? Why is it correct to do that? Well, the true thing is an infinite series here. But remember, if I apply b to some vector of length n, b to the power n applied to the vector gives 0. So in fact, if I multiply this, the infinite series, but I stop at time n, if I take the infinite series multiplied by this, I obtain identity, if my power series expansion is correct. But in reality, I don't have to worry whether this is a converging or not converging power series expansion, because in practice I will always stop somewhere. This is the interest of having these multiple representations. This is why filter calculus is so powerful. This is general philosophy of signal processing. In signal processing, we look at things in different representation and we use whatever representation is the most convenient. For filter, it's really an avalanche of different representations. We will see when there's a filter, there's always several ways to look at it. Some will give easy computation, some will give difficult ones. I've given 2 ways here to find the impulse response, for example, of the inverse. There are other ones. You could solve the equations here. You say, given x, I want to find y, then you have a recurrence equation. You can try to solve it and find a generic formula or a recurrence formula for computing. This is yet another method here. So we see that the power series expansion, the impulse response of the filter f is 1, 3, 7, 15, etc., which is not at all the same as 1 minus 3, 2. So in general, of course, they are completely different and hard to predict from one to the next. In practice, we don't work with arbitrary filters, but with filters that are convenient to work with. And filters that are convenient to work with are those ones here, the ARMA filters. So a moving average filter is a filter where such that the impulse response is finite. So there's only a finite number of coefficients, and hopefully typically small to make it pleasant to work with here. For example, delta 1, the derivative, the first order derivative differencing filter, is finite impulse response. It's y minus b, and then that's the n here. Its inverse, if I take the inverse of 1 minus b, there's multiple ways to find it. If I do the power series expansion of 1 over 1 minus b, I obtain 1 plus b squared plus etc., which is the integral filter. Right? If I apply this to a vector x, I obtain the sum of all the elements of x. Xt plus xt minus 1, etc. plus x1. Which makes sense, right? The inverse of differencing, which is a discrete time derivative, is the sum of all components, which is the discrete time integral. This one is not finite impulse response. All coefficients are 1. H are 1 always. So in general, a finite impulse response filter, also called a moving average filter, is something that has only p plus 1 coefficients. P is called the degree of such filter. It's often called a moving average because at least if the sum of the coefficient is 1, then it's truly an average of the current term and the past p terms. Right? So this is causal moving average. First category of filter. Second category, autoregressive filter. Autoregressive filter is the inverse of a moving average filter. So we say that a filter is autoregressive if its inverse is a moving average. For example, the integration filter is an autoregressive filter because it's the inverse of 1 minus b. So in general, an autoregressive filter will be something of the form 1 over a filter. Of course, the first element of the filter should be non-zero for the inverse to exist. And ARMA filter, which is a combination of autoregressive, AR, and MA for moving average, is the product of two. So it's F over G, where F and G are finite impulse response, which means also it can be put in the form of a rational fraction of two polynomials in B, in the backshift B. That's the generic ARMA filter. Those are the filters that most of the time we work with. Why? Well, because if we have filters with an infinite number of coefficients, it's hard to manipulate. So we like to have finite number of coefficients, but having only moving average filters does not give us enough power. If we want a filter that depends not just on the past P, but on the entire history of the filter, this is not sufficient. Whoops, sorry. So the autoregressive filter is a simple way to have something that depends on the entire past. In fact, we see here that's a filter that's introducing feedback. We're saying that the y at time t, the output at time t, is depending on the value now, the value of the inputs now, minus all these h1, etc., hp of the value of the output at the previous times, which then recursively implies dependence on the entire past of the filter. MATLAB's filter function implements exactly this. So for MATLAB, filter is equivalent to ARMA in some sense. Right? Here's an example. I applied the filter function of MATLAB, and I'm sure in Python there must be a similar one. The syntax of the filter function gives you the P and Q, which are the coefficients of the moving average, and the autoregressive parts, which are called the coefficients of a polynomial. And X is the input, so Y is the output. One way to understand it is to look at the input-output equation. When we use an ARMA filter, it means that the output, little y, is depending on the input through this equation here. Right? We must have that the first coefficient is non-zero, so very often we set it to 1, although in MATLAB it's not enforced. It doesn't have to be 1, but if it's 0, you'll have an error, hopefully. So here I set it to 1, and this is therefore the equation I have here. The polynomials that correspond to that are called the numerator and denominator polynomial. Now be careful, and that's the trick and the ugliness of signal processing. It starts always very beautiful and easy, and then you always hit a point where it becomes ugly. If you've done Fourier transform, there's always a point where the ideas are simple, but the details are ugly. Here is one of the ugliness that we have. The polynomial that we have, for example, if I look at this filter here, 0,1 plus 0,2b plus 0,3b squared. It's a polynomial in B, and the polynomial is the one that I wrote here. But what all signal processing people will consider the polynomial of this filter is obtained by changing the order of the coefficient. They will say that the polynomial is 0,1 x to the power 2 plus 0,2x plus 0,3. Right. This is why very often, if we don't want to do this change of order, we will consider that it's a polynomial in some formal variable called z minus 1. So you will see z minus 1 everywhere. Sometimes people will say this filter is 0,1 z minus 2 plus 0,2 z minus 1 plus 0,3 z to the power 0. This inverse here corresponds to also taking 1 over z. This also can be justified when you do z transform and stuff. We won't need that. We will not need Fourier or z transform for what we do here. For example, if I use MATLAB with this input polynomial, 0,1, 0,2, 0,3, 1 minus 0,2, it means I am simply writing the filter 0,1 plus 0,2b plus 0,3b squared divided by 1 minus 0,2b. So the vector y is equal to this operator applied to the input vector x. And the input-output equation is, the denominator polynomial is in the feedback term, yt minus 0 to yt minus 1 is equal to this thing here. So once we understand how it works, it's fairly easy to manipulate. I did here an illustration where I took a random x, so x is in blue. I took a random signal by calling random of some kind. Then I applied y, this filter to y. It's one line of MATLAB code, another line to plot it, and then I obtained this drawing here, which is the red is the output here. Then I asked myself, can I invert this? Is this filter invertible? Can we invert this filter here? Well, in this form, the answer is obvious. I mean, this filter is this filter divided by that. It means this filter multiplied by the inverse of that, right? So when is the product of two things invertible? Well, if each of them is invertible. So is the first one invertible? Yes, because there's a 1 here. If there would be a 0 here, the answer would be no. Is this one invertible? Well, it is the inverse of something already, so it is obviously invertible. And the inverse of f over g is g over f. So I can take the inverse of the filter PQ by doing filter QP. The only thing to verify is that the first coefficient of P is non-zero here. So I did that. It's, as you see, very simple in MATLAB to invert. I applied one more line of code to apply x to, there is the inverse of y is x qp. This should be y here. So I did that here. I took the blue, that's my x. I applied the filter, I obtained the red. And then I applied the inverse filter, and I obtained the green dots here. Which, so I put the blue line, but my signal is in discrete time. So in fact, the only values of the blue line that matters are where there are also green dots. We see obviously that the green is equal to the blue. The inverse of the image of x is x. Except here. After t equals 60, I'm starting having a problem. There's like garbage. The green does not correspond to the blue, and after some times I have an overflow problem. The green doesn't work anymore. Okay, that's one thing we need to be careful with about filters. What has happened here? What do you conjecture has happened? Well, in fact, we can see it by computing the inverse filter, computing the impulse response. So I did it by brute force. I asked MATLAB to compute. I created a vector imp, which is a very long vector of 1 with lots of zeros. And I applied filter PQ imp for this one, and for the reverse by QP imp. And I plotted on the y-axis the coefficients of the impulse response. The impulse response here is infinite because there is because of the denominator here. However, it decays exponentially fast to 0. So in fact, there's only a small number of terms that are non-negligible here. So it's an infinite response filter, but in practice, it's not very far from a finite impulse response filter. In contrast, for f minus 1, here, perhaps you don't see it, but this is times 10 to the power something, let's say 8, right? So all the values are extremely small, and then they become extremely large, right? Which sort of makes sense. If this decays exponentially to 0, this will grow exponentially to infinity, perhaps, although sometimes we can hope it's not true here. That's exactly the problem. It's easy to write a filter. It's easy to write the inverse, but we may find things like this because we haven't written explicitly the impulse response, but the impulse response is what matters. When I apply the filter to an input, I will do this calculation at time t. I will take a weighted sum of all the inputs with the weights being the impulse response. Now, if I take an arbitrary p and q, I might find this. I might find impulse response that have values that grow astronomically large. Now, what happens in MATLAB or in anything that does floating point computation, we'll have rounding errors. I'm multiplying numbers that are zillions, that are sometimes positive, sometimes negative. So if I take 1 zillion plus 1 minus 1 zillion, I will not get 1, but I will get 0, because this will be rounded with a fixed number, with a fixed precision. So that's the problem. The only way to solve that would be to do formal computation, symbolic computation, by, instead of taking values like 1 million, I take the fraction. For example, 1 over 3, I would keep it as 1 over 3 instead of 0.3333. Right? When I write 0.3333, after some point I do an error because the sequence of 3s is infinite. So it's possible. Some people do that. They do symbolic computation with filters. As long as you do only multiplication, additions, and things like this, you don't do square roots or other non-algebraic calculation, it works. But that's very, very, very slow. Right? So this is sometimes done. If you don't do it, you have to be careful with this. There is a well-known thing to know whether the filter we are doing will have this problem or not. It corresponds to what is called Bibo stability. Bibo means bounded input, bounded output. So a filter is said to be Bibo stable if, whenever the input is bounded, I give you an input vector y, where I know that y is less than some fixed quantity m. All components are y, less than some quantity m, whatever the length of y. Then if the filter is said to be Bibo, if whatever the length of y, if I take such an input, the output will also be bounded by some quantity. Which obviously will not be the case for such a filter. Because if I take a signal that's long enough, then I will start having numbers that become larger and larger. So the larger my signal, the more I'm lucky, I'm able to find values that are very large. So even if my input is all values equal to 1, for example, or between 0 and 1, let's say, I can always find an output that's arbitrarily large. So this one is not Bibo. And concretely, this means that a filter that is not Bibo stable is likely to cause numerical problems, accumulation of rounding errors, as we have discussed. So the simplest concept of stability for a filter is this one here. There are lots of concepts of stability, and if you take a course in circuits of system or control theory, you can spend your life studying various forms of stability, but we will not do that here. For us, the only concern that we have is the numerical stability, and this is captured by this requirement. Fortunately, we know exactly when an ARMA filter is stable or not. An ARMA filter has to do with difference equation. It's like a recursive formula can be written, how the output depends on the input. Right? Studying difference equations can be cast to matrix form, and then everything is related to whether a certain matrix, the eigenvalue of a certain matrix, are within, have a module less than 1 or larger than 1, because we will take powers of this matrix here. So to make this long story short, we won't go through the details of that, but you can easily find in signal processing textbooks the reason for that. The thing is, if I have an ARMA filter, the problems come from the denominator, right? The zeros of the polynomial, of the denominator of the polynomial, remember to take the polynomial, we inverse the order. The highest degree term is this one here. So we look at the zeros of this polynomial, and they are called the poles of the filter. And the filter is stable, Bibo stable, if it has no pole, because, for example, the order q is equal to 0, so that's a constant, there's no 0. Or all poles have a module less than 1. The poles, they are the zeros of a polynomial. In general, if you're not lucky, or in general, the roots of a polynomial are complex numbers. So we're interested in their module, the absolute value, but as complex numbers. And MATLAB's z-plane function will compute it for you. So I computed here the poles of my original filters, which are very easy. What are the poles? I have to solve the equation z minus 0,2 equal to 0. There's only one solution, it's 0,2. So it's here. Right? Now, if I look at the inverse filter, I have the denominator is what was here. So I have to solve the equation 0, 1z squared plus etc. plus 0, 2z plus 0, 3 equal to 0. So how do I solve this equation? Well, if it's degree 2, we know the formula, but the simplest is to ask MATLAB. And here are the two values I obtained. I plotted here or Z-plane plotted for me the unit circle. They're outside the unit circle, which will mean that this filter is not stable. In fact, what we will have in the impulse response will be made of powers, linear combinations of powers of the roots of this polynomial. Right? So the impulse response at lag k is a linear combination of all the roots of this polynomial, which are the eigenvalue of some matrix, to the power k. Right? Now, if the roots have a modulo less than 1, when k goes to infinity, z to the power k goes to 0, exponentially fast. Right? If modulo of z is equal to 1, then we're just at the boundary of stability, and we can work with such filters. Here, for example, I redid my experiment with this filter. P and Q are given here. So if I look at the denominator polynomial, the filter is stable because there is no 0. If I look at the reverse filter, I have to solve the equation 05z squared plus 03z plus 02 equals 0. And then I found two complex numbers that have a modulo less than 1. Therefore, it is stable. And in fact, I can see here that the impulse response decays to 0. So here, what I said 5 minutes ago was misleading. It's not because this is 0 after some number or decaying to 0 that the inverse should not decay to 0. Fortunately, there are lots of filters that are both stable and have a stable inverse. Right? Stability has to do with the denominator polynomial, and stability of the inverse with the numerator polynomial. So you can pick them independently. And of course, you have to pick polynomials such that both filters are stable. Typically, you want to work with filters that are stable, but also that have a stable inverse, because what we do with the filters is destruct something of the signal by using the filter to have something easier to work with, or that looks more like completely random noise, so there's nothing else we can say about it. But then we will need to reconstruct, go backwards. So we need the backwards to go backwards. So we need typically filters that are stable and have stable inverse. Last quiz of the day and of the week. And the majority says A, which is correct. That's in fact the definition of the filters, or one of the ways to define the filter here. This would be an incorrect interpretation of the definition. This is almost true, but it's not true. It's not y that is equal to x divided by this. Right? It's very tempting to write this, but this is not true. What is true is that y at time t is this 1 over 0,5 plus 0,3b plus 0,2b squared. This is an operator. That's the division of operators applied to the signal x instantiated at time t. This is the correct thing. Right? Voila, that's all for today for the calculus of filters. Next week we will see how we can use what we know now of filters to explain the forecast we can do once we have massaged the initial data with filters.